Assalamualaikum warahmatullahi wabarakatuh and hello everyone. In this video, we will learn about the spatial data and their nature. So at the end of this lesson, you should be able to understand what is spatial data, explain the nature of spatial data matrix, and describe the spatial data properties. So as an introduction, basically, spatial data is made up of coordinates that identify a location. So spatial data are geographically referenced or georeferenced. On Earth, they are referenced to a geographic coordinate system in terms of latitude and longitude. However, when displayed in maps, they are typically based on a projected coordinate system in terms of x and y coordinates. So these two spatial references system, which are the geographic coordinate system and projected coordinate system, are connected by the process of projection, which displays the Earth's spherical surface as a plane surface. So there are thousands of geographic and projected coordinate systems available that we can use. So, what is spatial data? Okay, geometrically speaking, the spatial data refer to either points, lines, or polygons, or the areas. The spatial interaction data record flows between the nodes or the intersection points of a network. These data are captured in an origin-destination matrix where the number of rows and columns of the matrix correspond to the nodes of the network, and the entry on row I and column J records the total flow from node I to node J. Okay. So this is known as the spatial tracking data, which records the movement of individuals or groups over time between areas or the nodes of a network. So the rows of the tracking matrix are the individuals, the columns are time period, and the entry on row I and column J records the location of individuals I in time period J. So this data can be used to estimate transition matrices where the entry on row I and column J of the transition matrix records the probability of any individual going from area I to area J in an interval of time. So in these two cases, the spatial objects remain fixed and motion take place over the static spatial backdrop. But over time, the point, line, and area features themselves can, for example, move, grow, shrink, speed, and change form. Okay, so it is another type of spatial data which records the attributes associated with spatial features, can be points or areas, that will be the focus here. So it has the following generic form, as you can see here, where capital ZJ denotes the J attributes, of which there are K, and the use of the lowercase zj denotes the measured value of the J attribute, and the terms SI and T denote the I point of which they are N, and the T time period of which they are capital T. And this define the location and time periods to which each attribute refers. So the georeferencing is associated with the SI, which are the location. So the generic form of the spatial data that we have seen before is often referred to the space-time data cube. So when T is fixed, then sometimes it is referred to the spatial data matrix with n rows corresponding to the set of location and k columns referring to the measured attribute. Okay, so I think you know about shapefile. So basically, shapefile is a digital vector storage format for storing the geometric location and associated attributes for each of the spatial objects. So we have the .shp that stores the geometry, while .dbf that stores the attributes. Okay, SDM attribute data may refer to properties for discrete entities such as people, business, houses associated to the point location. And the attribute data can also be in the form of counts of individuals located in the area, such as the number of people, number of employees, etc. So the data values are only true of entire areas and the variable is called spatially extensive. The spatially intensive, on the other hand, refers to the quantity expressed as ratio, proportion, or density, such as the population density, proportion of the workforce, and whatnot. The spatially intensive data values could be true for every part of an area if the variable was distributed uniformly. Attributes that are distributed continuously over an area are also defined as spatially intensive, such as the average level of the air pollution, the rainfall, and whatnot. So, next we will see how we can transform geographical reality to the spatial data matrix. So, basically, this transformational process can turn the real, continuous, complex geographic variation into a finite number of discrete bits of data that can be stored in a computer. So these are the sequence associated with the construction of the SDM for the three elements of attributes, space, and time. So the object and field views are the two fundamentally distinct conceptualization of the geographical reality, and the object view of the world conceptualizes the space as populated by well-defined, indivisible, and homogeneous entities for the points, lines, and polygons set in otherwise empty space. So the field view of the world conceptualize the space as covered by continuous surface. So the object view is often used to conceptualize social, economic, and demographic data, such as the houses, people, factories, roads, and towns, whilst the field view is often used to conceptualize environmental and physical data such as the rainfall, pollution, elevation, and whatnot. Although there is always some choice involved. Okay. So the process of representation is the process of discretizing space, that is, reducing this conceptualization to a finite number of geometric entities that can be stored in the computer, usually as points, lines, and polygon. So a field view can be discretized using sample points, contour lines, regular polygons, for example pixels obtained from remote sensing, or irregular polygons, for example vegetation patches. An object view is captured using the same geometric objects, but these objects are not always the same as the basic spatial entities that can make up the object view. So this process always involve a loss of information on spatial variability due to the smoothing of attribute values and simplification of objects, such as when we have like fuzzy boundaries, we want to make it becoming sharper and smoother than in reality they are. So sometimes it raises issue to the quality of the model as a representation of the underlying geographical reality. So the entities that are created by this process and which discretize the geographic space should ideally be well defined. So what does it mean by the well defined? So basically it is satisfactory for the context of what we want to study. For example, if there is individual level data, then although an individual person is well defined, providing a georeference may raise problem because people move about daily and may live in different places over the course of their life. So georeferencing people by their current residence might be satisfactory in the context of delivering health services to a population, but less satisfactory in the context of assessing population exposure to an environmental risk factor associated with a chronic disease, for example. And their attributes should be ideally internally homogeneous. So basically it should fit the purpose of what we want to study. Okay. So the final step of SDM's creation is the process of measurement by which attributes at particular location in space and time are assigned values. So the data values may obtained by a sampling process or by complete enumeration. For example, for the census, often they use the enumeration block. One way of thinking about the relationship between what is being measured and the recorded data value is that any data value is thought of as an approximation, subject only to measurement area, to some true value of the attribute at the particular space-time location. Different view of this relationship is that any value is only one possible value from distribution of possible data values, the so-called superpopulation reading in the spatial data. Underlying this later view of data values is the assumption that the underlying data generating model is stochastic, to which may be additional variation due to measurement area. So this view of spatial data is common in many areas of statistics and geostatistics. Even census data is sometimes analyzed with reference to a superpopulation. So the data is classified by level of measurement achieved. It can be nominal, ordinal, interval, or ratio. So the level of measurement determines what logical and arithmetic operations can be performed on the data, and hence, for example, what statistical procedures can be used. Therefore, there are two bases in classifying data types, which are the level of measurement and nature of discretizing object, which had been explained previously. In addition, in the map operation, it is also necessary to distinguish data between the spatially intensive and spatially extensive, which had been explained earlier also. So this is the level of measurement for the attribute data, the examples, and so on. Okay, next, let us see the quality of the spatial data matrix. So basically, the quality of the data in SDM is assessed given the chosen model for the SDM. The combination of model quality and data quality is sometimes referred to as defining the uncertainty of the relationship between the real world and what is held in the SDM. Data quality for all elements, which are the attributes, location, and time, is assessed in terms of four criteria, which are accuracy, resolution, completeness, and consistency. So there are a number of complications when considering spatial data quality, because it might vary across the map, being linked to interaction between the process of measurement and underlying geography, such as between the topography and the quality of imagery. Also, there can be interaction between locational errors, for example, attribute errors, errors during the georeferencing and whatsoever. Okay, so this is how we can transform the geographical reality to spatial data matrix. As we can see here, this is the real world. So we have the conceptualization and representation. So in terms of the attributes, space and time, and then we have the observation and measurement, and then we can get the spatial data matrix. But we need to consider the model quality. In terms of the data quality, we need to consider the accuracy, completeness, consistency, and resolution. And we need to consider the uncertainty of the relationship. Alright, next is the properties of the spatial data in SDM. Basically, there are three properties that we need to understand. The first one is the fundamental properties that refer to basically, in some sense, inherent in attributes that are distributed across the Earth's surface. Continuity is a fundamental property of attributes occurring in time, because so basically, it would be a strange world if attributes change suddenly and randomly from 1 second to the next, whether it was the weather or prices for commodities. Events occurring in time have an inherent continuity or structure, so that knowing what the level of an attribute is at one point in time allows us to make some informed estimate of what it will be at some future point in time. So this is the conceptual basis for making prediction. But the further into the future we wish to predict, the less certain we will be about attributes value. Right, continuity is the fundamental property of the attributes located in space. It is often referred to as a Tobler's first law of geography that we have learned last week. Basically, assessing the spatial continuity is quite complicated because it is relative to the time series case. By the second dimension, dependency might not be the same in all direction, and by the lack of directionality, because time has natural unidirectional flow from past to present. We do not have like multi-directional, because time always from past to the present. So basically, the idea of continuity translates in the spatial context as the measurement of the same attribute taken at several locations in geographical space will show evidence of correlation or autocorrelation or the self-correlation. So what does this mean? Basically, if the value for an attribute at one location is high, so it is probable that when the same attribute is measured at a nearby location, that the value too will be high and vice versa. This denotes positive autocorrelation. So as the distance separation of observation increases, such autocorrelation will tend to weaken until at some distance observation on the same attribute will appear to be independent. So this is the concept of the spatial autocorrelation, which we will learn in few weeks time basically. But it used the first law of geography concept. Alright, basically, a distinction should be drawn between autocorrelation in the case of entities in an object view of the world and in the case of a field view of the world. So, because in the case of distinct entities, it is possible to conceive a complete spatial randomness in their attribute values and indeed negative spatial autocorrelation between adjacent neighbors. Okay. Quantifying and testing for the significance of spatial structure was an important research agenda during geography's quantitative revolution. Basically, statisticians such as Moran, which come up with the theory of the spatial autocorrelation, Jerry, Krishna, all had developed tests for the presence of the spatial autocorrelation on regular lattice system. A number of geographers such as Dacey, Cliff and Ort adapted these statistics to the situation usually encountered in the social sciences where data are collected from an irregular spatial partition or irregular distribution of location. Right, the next one is the properties due to the chosen representative. Basically, how the fundamental properties of a spatial distributed attribute are retained in the SDM will depend on the chosen representation. So if a surface is captured using point samples, then the extent to which the underlying structure is captured will depend on the density of the sample points in relation to the surface variability. So if polygons are used, it will depend on the size of the polygons in relation to the surface variability and whether the polygons represent an artificial or imposed grid or follow the natural boundaries. So there is a loss of information which follows the consequence of sampling and discretizing. Next is the properties introduced through the measurement process. So basically, how the process of taking measurement might introduce false properties into a spatial database. So basically, locational error may induce attribute error with overcounting in one area matched with undercounting in another area because a case has been attributed to the wrong area. Such errors are often relatively short range, so it is possible that the errors in counts are negatively autocorrelated with an undercount in one area matched with an overcount in an adjacent area. So false clusters of cases of events can be induced if geocoding follows some convention. So data on different attributes may have been collected on different spatial frameworks and then have to be put onto a common spatial framework by aggregation. Uh, Important class of spatial data is compiled through a process that starts with a continuous and complex reality and concludes with the construction of the spatial data matrix. So spatial data have properties, some deriving from the fundamental nature of the geographic reality, others acquired through the representational and measurement process that follow. So those properties and the resulting quality of spatial data provide an essential context within which methods for analyzing spatial data are developed and results interpreted. Okay. So equally important are the types of questions that often asked. The inference problems faced, including the spatially structured models built to understand the world. So it is these models and how they are constructed that determine the model for the spatial data matrix, that determine in any particular scientific context what data are needed, at what scales and according to what configurations. Alright, so these are the references that I've used to prepare this lesson. So you may refer to it. Okay, I think that's it. Thank you so much for listening. Till our next lesson. Assalamualaikum. Bye bye.